This farmer has a fox, a chicken, and some sweet corn. And he wants to take them all across a river, yet he can only take one in his boat at a time. And if he leaves the fox and the chicken alone, the fox will eat the chicken. And if he leaves the chicken and the corn alone, the chicken will eat the corn. Now, can you think about how we can do this? This is called problem solving. Problem solving is like an algorithmic puzzle, and there are a couple of ways that we can solve these puzzles, either a specific or general case. A specific case is where you have 3 by 3 magic square, whereas a general case is you have an n by n magic square. Now, I'm not going to go into great detail in this video about the magic square problem itself, but I'll use it as an example so you can see the sheer number of computations that are needed when you use what's known as exhaustive search. Suppose you're asked to fill a square with 3 rows and 3 columns with distinct integers in the range 1 to 9, so that the sum of each row and each column and all the diagonals all add up to the same number. Okay, so whatever's here, whatever's here, whatever's here, comprendez-vous? They all add up to the same number. Exhaustive search is a process of just randomly putting them in any order, these numbers, because they're distinct, right? So I'm just going to do it in this order. Putting it in like that until you get the point in which all of these add up to the same number. Now, it's called exhaustive search for a reason, because it's bloody exhaustive. And because there are 9 different 3 by 3s, nine different squares, or places within this square that you could go to, you have this calculation called 9 factorial, because you have 1 times 2 times 3 times 4 all the way to 9, you understand, which is a really, really high amount of calculations. To be specific, this calculation shows us there are over 360,000 ways that we can arrange the integers within this particular box. And you may think, well, come on, a computer that does lots of computations per second should be able to do that. Well, let's say the box is bigger. 5 rows and 5 columns. It would take a computer, performing 10 trillion operations a second over 49,000 years. 49,000 years to work out all the operations of what you've now got, because 5 times 5 is 25 factorial. 49,000 years to work out. So we understand that exhaustive search is probably not the best way to go about problem solving all the time. So what else can we do? We have a faster solution known as divide and then conquer, or binary search. So if you've never seen or come across binary search before, you're going to love this. Right, so we're looking for a particular integer in this list. So this list is a sorted list, right? So it's in the right order, 7 to 25. And we're looking for a particular integer. Say, for example, in this case, it is 12. So what you do, divide and conquer, pretty obvious by the name. We divide it, but we start by looking at the middle integer. Now, in this case, the middle integer is going to be either 13 here or 13 there, because we have an even amount of elements in our array, and therefore we're going to just take from base 0 to 5, because that's how we work in computer science. We index from base 0 rather than 1. So this is the first index, the first element, 0. We're going to go 0, 1, 2. We could have also taken 3, but obviously it depends. Actually, you know what, in theory, let's take 3, because we round up. If it's 2.5 in the middle, then we round up to 13. So 13, right? Is it the number we're looking for? No. Is the number we're looking for higher or lower than 13? Well, we're looking for 12, and obviously 12 is lower than 13. So what we can really do now is know that this one is not our number, but then everything above it is also not our number, because it's lower than the number we're at. Right, so we've divided, and we've conquered, because we've worked out it's this half that we want, because it's lower. Remember, this is a sorted array. So we don't need any of these. What's the point of having them? Right, so now we've got 1, 2, 3. 3 more. Let's take the middle one. Right, is it the number we want? Yes. Bang on, right? That was 2 goes. 1 here, and let's do 1 here and 2 here. We've already got the number we were looking for. Right, now let's do this again. Say we're looking for 25. So we take our 13. We look at it. Is 25 higher or lower than 13? It's obviously higher. So we clear out all these ones here. Now let's, for argument's sake, let's say we look at between 13 and 25 now, and at the middle integer. It's 17. Is 25 higher or lower than 17? It's obviously higher. So we've only got one integer left now, and it has to be 25. So 1, 2, 3 steps. 3 steps in binary search. Imagine if we were doing exhaustive search. Do you remember exhaustive search? It's only 10 minutes ago. 1, 2, 3, 4, 5, 6, right? If we start from the bottom in an ascending sorted list, we would have to go 6 times to find our key value. It's one of the quickest ways to find out where something is within a sorted array. Did you forget about our farmer? Right, let's look at how we solve this problem. So, he picks up the chicken first, takes the chicken across with him to the river, leaves it on the other side. Then, he comes back over, grabs the fox. Now, obviously, he can't leave the fox and the chicken there, so he picks up the chicken and takes the chicken with him. Drops off the chicken, grabs his ridiculously oversized sweet corn, takes it back on the other side. Now, the chicken's not going to eat, the fox ain't going to eat that, is he? He doesn't like that. He's waiting for the chicken, and lovely. Brings them all over, he can keep an eye on them. And now, obviously, he goes home and has a lovely chicken dinner. I'm playing around with different designs, and I do appreciate feedback if you like it, if you don't like it. Thanks for watching regardless. Bye.